This video is about light and spatial relativity and some background about it, and also we will discuss Einstein's postulates. So first of all, to start, we need to understand what's a frame of reference. So a frame of reference describes where an observation has been made from. Sometimes this may be coming from a stationary point of view, or the frame of reference itself can be moving. The best example can be a person sitting on the earth and looking at a plane flying. So the frame of reference of the person is stationary, but the observation is made at the plane which is flying up in the sky. A person sitting in the plane is at rest for the fellow passengers because they both are in the same plane which is moving at a constant speed. All right. When we say something is moving, what we mean is that its position relative to something else is changing. A passenger moves relative to an airplane. The airplane moves relative to the person sitting on the ground or the earth. Earth moves relative to the sun. Sun moves relative to the galaxy, and so on. There is no such thing as absolute motion. Everything is relative. All right. It can sound philosophical, but yeah, everything is relative. There is nothing like absolute motion. All right. In such cases, the frame of reference forms a descriptive part of the motion. There are two types of frame of references. First is inertial, another is non-inertial. The inertial frame of reference, as the name suggests, inertial. So the law of inertia holds good in this inertial frame of reference. So the frame of reference in which Newton's first law of motion or law of inertia holds is called inertial frame of reference. And of course, non-inertial frame of reference is in which law of inertia does not hold. Okay. Another difference between inertial and non-inertial frame is that inertial frame of reference doesn't have an acceleration. Either the frame of reference, for example, if I'm going in a car which is going at 60 kilometers per hour, then it's at a constant speed, constant velocity. There is no acceleration. And when there is no acceleration, I'm in an inertial frame of reference. But if I'm going 0, 20, 30, 40, 60, 80, coming back to 60, coming back to 40, then I'm changing my velocity. Then I'm in a non-inertial frame of reference. Okay, so whenever I will say inertial frame of reference, please keep in mind that velocity is constant, so there is no acceleration. Okay, now the Earth is considered as inertial frame of reference because it moves at a constant velocity and it is such a big mass and it has such a high gravitational pull that it is considered as an inertial frame of reference. You may argue that as it is changing direction as it is moving, so why it is not considered as accelerating? But no, this is an exception we make, that Earth as a whole is considered as inertial frame of reference. So if I'm sitting on the Earth, we usually have seen in the questions previously which we have done that we say that it is at rest, because we consider when I'm sitting here in my house and making this video, I'm at rest. But if a person from the space will look at me, he will see me moving with the Earth, right? So this is frame of reference. For me, I'm at rest. For that person from the space, I'm not at rest. Everything is relative. All right. We will consider in this special relativity only inertial frames of references. When we talk about general relativity, then the non-inertial frame of references comes as well. But for the course of physics that this video is for, only special relativity is included. So I will not talk much about general relativity here. Now, consider an object moving in a frame of reference A. For example, let's say, I'll tell you with an example that will be better, that if I'm sitting on a platform, train platform, and a train is passing by, all right? And let's see, it's a see-through train and I can see in the train. It's a thought experiment. A thought experiment is an experiment where we just think how the things will be. It's not actually done. It can be done, but right now I'm calling it as a thought experiment with a see-through train. All right, so there is a person standing there and the train is going towards my left at a speed of 20 meters per second. And there is a person inside the train also running inside the train towards my left at a speed of 5 meters per second. So what is the velocity of that person relative to me, which is standing on the platform stationary? All right, so that will be given by, because they are both traveling in the same direction, so 20, because that is the train's velocity as per the ground, and 5 meters per second, that is person's velocity relative to the train. So 20 plus 5. I will see, when I look at that person, I will see he's running very fast, 25 meters per second. Because the train and the person, they both are moving here and the frame of reference is outside. All right, let's change the direction of the man. Let's say now the man has decided, no, I want to go towards the right. And the train is traveling towards the left. So what will happen? Then I'll see now the person is running slowly. So the relative velocity of the man, when I look at him as an observer outside the train, it will be 20 minus 5. Okay, I will upload my notes and I have done the same question in my notes. So there shouldn't be any issue. If there is, let me know. This is relative velocity. We have done a bit of it in year 11, not much, but it's not difficult. All right. Now, what will happen if I am in the train with that man? And if he is running from here to here 5 meters per second? For me, when I am in the same frame of reference, that is inside the train, the velocity will be 5 meters per second. There will be no change, because now for me, I am in the same frame as the man. So I will not consider the train's movement. But when I'm outside and another frame of reference, it matters to me that he is running in a moving train and in which direction. All right. Now let's go back to a little bit of history about special relativity. Special relativity theory was developed by Einstein in 1905. He was only 26 years old. And this theory was extremely important because it fundamentally changed how we understand the structure and nature of space and time, and specifically how different observers perceive different things in different frames of references. All right. Before this, we had Newtonian view in which space and time are absolutes. Everyone's time will tell the same time. Everybody will exactly say what the space is, what the time is. But not in the case, that is not the case with the relativity. In special relativity, the view is very different, where space and time are not at all absolutes, but they are relative to the frame of reference or to the observer who is observing it. All right, there are the term special relativity. The term special is used only for inertial frames of references. If I say general relativity, it will include the non-inertial frames of references as well. In special relativity, we will see time dilation, we will see length contraction, we will see many different strange, weird phenomena which can boggle your mind. So be prepared for a very beautiful journey of special relativity. All right. Before diving deep into special relativity and these weird phenomena, let's have a little bit more background about the physics and what was going on at that time that led Einstein to develop this theory. In 1860s, Maxwell developed Maxwell equations, which described electromagnetism, electromagnetic waves, and he gave us a value for speed of light, c, equals to 3 times 10 to the power 8 meters per second. What these equations couldn't give us was what the speed is relative to. As I said, everything is relative. If I move in an aeroplane which is going up, then I move as per my fellow passenger, right? But for a person sitting on the ground, it's just plane that's moving with all the passengers inside it. So the speed of light c, which Maxwell gave, What is relative to? The equations couldn't tell us. Different observers might disagree on how fast an object is moving depending on their perspective, like the train example. If I'm in the train, the person is just going 5 meters per second. If I'm outside, then either he's going 25 or 15. So different observers might see if the thing is going fast or thing is going slow. So when the Maxwell gave this value of c as 3 times 10 to the power 8, people were thinking, what is it relative to? All right. This led the idea of ether, AETHER, ether. That because they say that sun's light is coming to earth, so light is traveling, and at that time they were not very sure that electromagnetic waves can travel through vacuum. So they thought, no, there should be some media in the space, which relative to which the speed of light is 3 times 10 to the power 8 meter per second. So they named this material as ether. All right, that this is the background material, and this allows the light to propagate through it in the same way as air helps the sound waves. All right, so this was the notion. Now, different experiments were performed to observe the change in speed of light as per the direction. Because if the speed of light is going in the direction of ether, it will be higher, c plus v. If it is going opposite to the ether, it will be c minus v. V is the, let's say, velocity of ether. Okay, like the train example, going with the train plus, opposite minus. So they did many experiments. How they did, it's a very famous Michelson-Morley experiment. You can Google about it or read it from your books. What they did, when the earth moves around the sun, so for half of the time the earth is going like this, and then it's going like this. For example, let's say the direction of ether is from my left to right. Okay, so when earth is going like this, it is going opposite the ether, and when it is coming like this, then it is towards the ether. So they tried to measure the light during this time period of the earth, and then after 6 months, this time period of the earth. No change. Zero change. The speed of light was always 3 times 10 to the power 8 meter per second. So eventually they gave up on this idea of ether. They said, nah, there is no ether. It's not ether because there is no difference in the speed of the light. So there is no material such as ether. This is the background that they considered this hypothetical material, ether. Now, after all these things, Einstein came up with his own postulates. What's a postulate? Postulate is a statement made which is assumed to be true. Now, it's not that I'll say any statement and I will name it as a postulate. It has to be backed up by proper research and explanation. Then only it becomes a postulate. So Einstein gave two very important postulates which changed. These are the bases of special relativity. The first is that law of physics are the same in all inertial frames of references. I'll repeat it. The laws of physics are the same in all inertial frame of references. What does it mean? It means that we do not have any preferred frame of reference. Everything is relative, right? So if an object is moving inertially, then there is no experiment that can say that this object is moving, this object is stationary, or vice versa. No, everything is relative. And if it's an inertial frame of reference, all the physics will go on same. Okay, so all of the laws of physics should be exactly the same for any inertially moving object. We do not have any preferred frame of reference. This is first postulate. Why is this first postulate? As I said, I'm stationary on earth for the person sitting next to me. But for a person looking from space, I am moving. For me, the plane is flying. Okay, if I'm sitting in the plane, everybody is at rest for me. So everything is relative as long as we are in inertial frame of reference. The second postulate which Einstein gave was that speed of light is a constant. no matter even if the source of the light is moving or not. Okay, for example, I have a torch. Okay, if I turn on the torch and if I measure the speed of the light coming out of the torch, what it will be? 3 times 10 to the power 8 meter per second. If I start moving forward with the torch, will the speed of light change? Will it become c plus v? No. If I move backwards, will it become c minus v? V being my velocity or the velocity with which I'm moving torch. No. Speed of light is a constant one. This was the second postulate, and this is very important. Why? Because we will be learning about length contraction, time dilation, twin paradox, whatnot. So this is all about special relativity. There are a few more things. Yep, that is it for this video. All right, take care. Bye.